Good afternoon, everyone. Today we will be presenting our Phase 3.5 project on gait-based walking condition classification using the casia dataset. Our group members are Zachary Cathart, Bryson London, and myself, Alondra Wilson. The main focus of this project was using deep learning and computer vision techniques to analyze human walking patterns. Specifically, our goal was not to identify a person's identity, but instead classify the condition under which they were walking. The three conditions we focused on were normal walking, carrying a bag, and wearing a coat. Over the semester, we first studied how gait recognition systems are used in modern speech, then replicated a baseline study inspired by Open Gait, and finally, improved that baseline during phase 3 using better pre-processing, validation strategies, regularization, and training optimization. One important aspect of this project is that we wanted to balance both performance and reproducibility. Many modern gait recognition systems use extremely large transformer models or complicated multi-model architectures, but our goal was to create a pipeline that was still effective while remaining understandable and reproducible. Before discussing the model itself, it's important to understand why gait recognition matters and why this problem is meaningful. Gait recognition is the process of analyzing the way a person walks in order to recognize or classify information about them. Unlike facial recognition or fingerprint systems, gait recognition can work from a distance and does not require direct cooperation from the subject. This makes it useful in surveillance environments, security systems, smart authentication, healthcare monitoring, rehabilitation analysis, and even behavioral studies. One reason gait recognition is challenging is because walking patterns can change under different conditions. For example, carrying a bag changes balance and posture, while wearing a coat changes the silhouette shape and partially hides body movement. These changes can reduce model accuracy if the system is not robust. That leads directly to our project goal. Given a silhouette walking sequence from casia B, our task was to classify whether the subject was walking normally, carrying a bag, or wearing a coat. This problem is important because it focuses on robustness. Real-world gait systems need to perform accurately even when people wear different clothing or carry objects. So instead of focusing on identity recognition, we focused on condition-based classification. Project, we used the casia gait dataset, which is one of the most widely used benchmark datasets in gait recognition research. The dataset contains gait sequences from 124 different subjects captured under 11 camera viewing angles ranging from 0 degrees to 180 degrees in 18-degree increments. Each subject has multiple walking sequences under three conditions: normal walking, carrying a bag, and wearing a coat. The main modality we used was silhouette image sequences. These silhouettes isolate the human body shape and movement while removing unnecessary background information. This allows the model to focus primarily on gait dynamics rather than color or texture. The target label included both walking condition and view angle. For our classification task, the three classes were NM for normal walking, BG for carrying a bag, and CL for wearing a coat. The dataset also introduced several important challenges. First, viewpoint variation means the same walking motion can look very different depending on camera angle. Second, appearance changes caused by bags or coats significantly alter silhouette structure. Finally, pre-processing quality is extremely important because poor normalization or inconsistent frame handling can negatively affect performance. To improve generalization, we used a subject-based split instead of randomly splitting sequences. Subjects 001 through 024 were used for training. Subjects 025 through 030 were used for validation, and subjects 031 through 036 were reserved for testing. This ensured that the model was evaluated on completely unseen subjects, which creates a much more realistic testing scenario. In our literature review, we analyzed research trends from approximately 2020 through 2025 related to gait recognition and gait analysis. One major trend we observed was the movement away from traditional gait energy image methods toward deep learning-based approaches. Earlier gate systems often relied on handcrafted features or static image representations, while newer systems increasingly use CNNs, temporal modeling, transformers, and fusion-based architectures. Another important trend was the growing emphasis on temporal modeling. Many researchers moved away from treating gait as a single image and instead focused on analyzing motion patterns across entire walking sequences. This makes sense because gait is fundamentally a motion-based problem. We also observe strong interest in global local feature learning. Many modern architectures divide the body into multiple regions so that the model can separately analyze upper body motion, lower body movement, arm swing, and leg motion. Examples of this include gait cart and gait GL. At the same time, we notice several limitations across the literature. Many transformer-based or multi-model models introduce extremely high computational complexity and require very large training data sets. Other approaches depend heavily on estimation pipelines or optical flow extraction, which makes them harder to reproduce and more sensitive to pre-processing errors. Because of these limitations, we selected an OpenGate inspired baseline. OpenGate stood out because it provided a standardized, reproducible, silhouette-based framework that could realistically be replicated and extended within the scope of this project. In phase two, our main objective was building and validating a working baseline pipeline. The baseline training configuration used 20 frames per sequence, 10 training epochs, the atom optimizer, and cross entropy loss. The pre-processing pipeline standardized silhouette sequences and generated gate representations that could be passed into the CNN model. The classification task focused on distinguishing between the three walking conditions: normal walking, carrying a bag, and wearing a coat. The baseline architect followed an OpenGate inspired design. The model extracted spatial features from silhouette frames, aggregated temporal information across sequences, and then performed classification. One of the key ideas behind the baseline was preserving temporal motion information instead of relying only on static images. This allowed the model to learn movement-based patterns that differ across walking conditions. The baseline achieved approximately 76.97% accuracy on unseen test subjects. While this result demonstrated that the pipeline was functional and capable of learning meaningful gait features, it also highlighted areas for improvement. We noticed that some classes were easier to separate than others, especially under appearance variation. Okay, this slide provides more detail about the baseline performance and evaluation. The baseline model used a CNN-based classifier trained on silhouette sequence representations and evaluated performance using accuracy, position, recall, F1 score, and confusion matrices. Overall, accuracy ranged around 75 to 80%, with the official baseline result being approximately 76.97%. The strongest performance occurred on the bag condition. Carrying a bag introduces clear silhouette changes and shifts in posture that the model could learn relatively effectively. The coat condition proved more difficult because coats alter the overall body shape and hide finer motion details. This increased overlap between classes and created more confusion during classification. The confusion matrix showed that the model was generally learning useful gait features, but some overlap still exists between normal walking and coat conditions. These observations became important because they directly guided the improvements we implemented during phase three. In phase three, our focus shifted from simply replicating a baseline to improving both performance and generalization. The first set of improvements involved the data pipeline. We improved the subject split, added a dedicated validation set, removed invalid or corrupted sequences, and increased the number of frames from 20 to 30. Increasing the frame count allowed the model to capture more temporal information from each walking sequence. Next, we improved the training process. We increased the number of epochs from 10 to 40 so the model had more time to converge. We added dropout regularization to reduce overfitting and switched from the Atom Optimizer to Atom W, which provided better weight regularization and training stability. We also implemented a learning rate scheduler so the learning rate could gradually decrease during training, helping the model fine-tune its parameters more effectively over time. Another major improvement was validation-based model selection. Instead of simply using the final epoch, we saved the best performing model checkpoint based on validation accuracy. This helped prevent overfitting and improve final test performance. Overall, our improvements focus on optimization, reproducibility, and generalization rather than drastically increasing architectural complexity. Our updated architecture remained based on OpenGate-inspired sequence processing pipeline. The first component was the CNN backbone. This included convolutional layers, batch normalization, re-LU activation functions, and max pooling operations. These layers extracted spatial features from each silhouette frame. After frame level features extraction, temporal aggregation was applied across the sequence dimension. This allowed the model to combine motion information over time and better capture gate dynamics. The next component was the horizontal pooling pyramid, or HPP. This module divided the feature map into multiple horizontal body regions at different scales. By doing this, the model could separately analyze localized motion patterns from different body parts, such as the upper body, torso, and legs. This was especially important because different walking conditions affect different regions of the body. For example, carrying a bag may affect upper body balance, while wearing a coat changes overall silhouette shape. Finally, we added dropout regularization and Atom W optimization to improve generalization and reduce overfitting. One important design choice was keeping the architecture relatively lightweight compared to modern transformer-based systems. Our goal was achieving strong performance while still maintaining reproducibility and manageable computational requirements. After implementing the phase 3 improvements, the final model achieved 85.30% accuracy on the held out test set. This represented a substantial improvement over the original 76.97% baseline, showing that pre-processing quality, training strategy, and evaluation methodology had a major impact on overall performance. The final evaluation included 660 test samples, with 563 correctly classified predictions and 97 incorrect predictions. When analyzing class-specific performance, the bad condition achieved the strongest results overall. The coat condition remained the most challenging because coats significantly alter silhouette structure and reduce visibility of body motion. The confusion matrix showed that the majority of predictions fell along the diagonal, meaning most samples were classified correctly. However, some confusion still occurred between normal walking and coat conditions due to overlapping gait patterns and silhouette similarities. Overall, these results demonstrated that our improvements successfully increased generalization and classification performance without requiring extremely large transformer models or highly complex multi-model architectures. This slide summarizes the contributions of each team member and the final status of the project. Bryson primarily focused on dataset pre-processing, gate energy image generation, sequence handling, model implementation, and training improvements. I focused on literature review, dataset analysis, and documentation. Zachary contributed to evaluation, results analysis, testing, and report writing. At this point, we successfully replicated a baseline OpenGate-inspired pipeline, implemented multiple phase 3 improvements, and increased overall performance to approximately 85% accuracy on unseen test subjects. One important takeaway from this project is that strong performance can still be achieved using relatively lightweight and reproducible architectures. Many recent research papers rely on transformers GANs, or multi-model fusion systems that require large amounts of computation and pre-processing. Our work showed that carefully designed pre-processing, temporal modeling, validation strategies, and structured feature extraction can still produce strong results without excessive complexity. Overall, this project demonstrated the effectiveness of sequence-based gait analysis for walking condition classification and provided a strong foundation for future improvements such as in-symbol learning, transformer integration, or multi-model fusion. Thank you.